probably about a minute or two away from starting. So just before we do, and we've got a few people coming on board, we'll just do a couple housekeeping reminders. If you haven't already done so, if you could please make sure that your microphone's muted during today's session, it's greatly appreciated. Just cuts down on the background noise. And we'll probably wait maybe one more minute before we start the presentation and introduce today's speaker. So we'll just be getting underway shortly, but welcome everybody for those who have joined the meeting and the session, and we'll be getting underway right away. Thanks. All right, it looks like we've got a host of participants who have now joined, so we'll get underway. Good afternoon, everyone. My name is Lanny McGinnis. I'm President and CEO of the Manitoba Home Builders Association. And on behalf of our event sponsors, the Accurate Technology Group and Federated Insurance, welcome to the second MHBA virtual technical session being held this month. Thank you to all of you for attending today's webinar. Just before we get underway, just a few housekeeping reminders. Please make sure you got your microphone muted. Just avoids any background noise during today's presentation. And if you do have any questions, just as we did in our last session, please use the chat function, which is the little speech bubble at the bottom of your screen there. You can type in any questions that you have during the presentation. Darrell's happy to take those. We're monitoring the chat and we will raise them as they come in. So please feel free. Last session, we had a lot of great questions for Darrell, so that's most appreciated. And now let's kick off today's session with a quick introduction of today's speaker by our great event sponsor today, Federated Insurance. So take it away, Curtis.
Hi, good afternoon, everyone. My name is Curtis Chuby from Federated Insurance. We're today's sponsor of the webinar, and it is our pleasure to introduce the speaker, Darrell Paul. For over 40 years, Darrell has been involved in residential construction from framing to supervising, and today running Qualistat Building Performance Consultants. Darrell has partnered with the BT Group to provide package design and diagnostic services, including hydronic and mechanical engineering, NECB and 9.36 energy compliance, energy efficiency, and of course, building envelope designs in residential wood frame multifamily projects, including engineering services. With offices in Calgary, Olds, Edmonton, and Nanaimo, BC, they also perform diagnostic testing for forensic and warranty claims. Darrell has spent the past 20 years in building envelope and taught at the Southern Alberta Institute of Technology Moisture Control course for 14 years. He has lectured throughout Canada on performance-based envelope designs. The third edition of the Building Envelope Tie in Details book, written for the Siding Contractors Association of Alberta, will be available shortly. It's my pleasure to introduce Darrell Paul, everyone.
Thanks, Curtis. Appreciate that. So let's get this presentation up here. And we'll get rolling. All right. Give it a second to get, there we go. So a couple of weeks ago, we did a presentation on the second plane, or the drainage plane. And so this kind of goes hand in hand with that. It gets into a little more detail with respect to various cladding materials. But this is dealing more with how the building envelope and cladding work than it is with, specifics for architectural designs or things like that with regard to various claddings. So we want to look at the building science perspective of this. When we go through this presentation, as was mentioned, if you have a question, at the time you have the question, either throw it into the chat and let Andre know, and he can fire it out to us, and we can cover that. It's a little bit easier, a little more interesting that way. So our learning objectives today, what we want to put together is an idea of how our claddings are affecting the connections or transitions with other claddings. We want to look at how they tie in with windows. We want to look at the system, how each system of cladding performs. We look at the drainage and drying ability. Those are two key things that when it comes to claddings. And then practical applications and some case studies, some examples. You'll notice there we have, where's this mouse here? You notice there we have the little Instagram for Qualistat Building. So if you have any time and you want to have a look at that, we've got all sorts of videos and what to do and what not to do, kind of little tips on that. Really short, simple, concise. So when we're talking about exterior claddings, we're talking more about the assembly with the cladding than we are just the cladding. So here on the right, you see the assembly right here, but over here on the left, you see just the cladding itself. So if we only focus on the cladding and the paper or the weather barrier we put behind it, then we kind of lose out on the whole assembly. And the reason that we want to talk about the assembly is because the building envelope, or the separation between interior and exterior, that conditioned space, really is affected by how the assembly performs. So rather than just adding a component to the exterior and hoping it works together, we want to build that assembly so that it performs all together as one independent structure. So we've got the structural components, we've got bulk water management, vapor, air, and thermal management, and we manage those things together. And we can't really separate the cladding from the interior. So I'll give you an example. If you look at a cantilever here, on the left, we have the traditional fiberglass insulation, and we've got an air barrier outside of that. But if we have the insulation installed here already, we want to have a really robust air barrier around the perimeter. So really airtight, because there's no way the insulator is going to get in there and make sure that that I-joist is perfectly sealed. So one of the things we went to is we went to spray foam. So now we've added an additional cost, but at the same time, we've made it more airtight. So what are the difference between those two assemblies when it comes to installing materials? Well, we want to discuss that with our insulation contractor, maybe with our framer, maybe with our cladding contractor, and how does that assembly perform differently when you have fiberglass versus when you have spray foam? And so by understanding how it performs and then looking at what claddings we're putting on, is it a very airtight cladding? Is it a very permeable cladding where air can flow through? Is it a vapor barrier type cladding where we need some more air to get rid of the moisture buildup? All of those things. So we want to be able to understand the whole assembly. So we look at the assembly or the system as a whole here. We want to make sure we look at the system, and that way we get the best bang for our buck. We can adjust things in various locations, but we're going to get it to perform as well. Now, if we break this down into the three main, building science components, we look at the air and what impact air has on exterior claddings. So for instance, what does wind or wind-driven rain and the pressure drop that creates have on the impact of moisture sitting on the outside of a cladding, which gets sucked through the wall? What about the drying time needed? What about diffusion? If it's not able to air dry for air blowing through, it has to have the ability to dry by means of diffusion. So those are all critical components of our exterior cladding. When we get to the moisture aspect, we look at the ability to absorb and hold water. We look at capillarity and vapor drive, vapor moving through a material. We look at the ability of it to drain and get rid of the water so that we don't get hydrostatic pressure. But there's also this expansion contraction component where, if we get a material in behind a cladding with a cladding that is going to expand and contract, what does that do to its water shedding capabilities? So that has to be addressed. And then finally with heat, the more insulation we put within the building, the less heat loss we have. So that's going to affect condensation, frost forming within the assembly, especially the exterior components. That could affect the energy efficiency depending on how much air goes through. And even the drying ability of that material that we put on the outside. If it doesn't dry very well, is that a relationship between the insulation and the location of it and our cladding? So those are all things that we like to ask and think about. But to start with, let's go back to the very basics and say, okay, well, what's our wall assembly? In Canada, we typically build with framed wall versus mass wall, especially with mass wall, concrete block and brick materials. Typically in residential, we don't see a lot of that. So the only mass wall we typically see is an ICF block. So what's the difference between a mass wall and a framed wall? Well, short and sweet, it's really got to do with the materials that we put on the exterior over top of these materials. So what's the risk on the left of this framed wall getting water within it, having deterioration occur on the sheathing? It gets wet, starts to grow things, it rots, it doesn't like water, it likes to stay dry. On the right, when we have a mass wall, we have really no thermal bridging, and we have no problem with moisture getting in there, because what's the worst that could happen if you have wet concrete? It just gets harder and harder. So there is some unique differences between the two. But we're going to focus on the left during this presentation and talk about, framed wall assemblies. So when it comes to framed wall and the ability to hold on to moisture or attract moisture or get rid of moisture, we need to understand with the claddings how it handles moisture and how it deals with moisture. So for instance, here, if we're looking at the abilities of an exterior component like stucco, we have a cementitious stucco. Well, it's a hygroscopic. It's a material that will absorb water and hold on to it, versus something like a vinyl siding, which is hydrophobic. The water hits it, it sheds off, the water gets through, it runs down the back of it. They're very different materials, but knowing which materials absorb and hold on to water is important, because when they're in contact with the weather barrier behind them, which is in contact with the wood sheathing, then what impact does that have on the way it performs? So understanding that is very important. Now down here, we talked about composite materials and Efus materials. So a composite material in the context of what we're talking about would be a material that's recycled, but it's got wood material in it. It's not just pure plastics. So when we talk about it being an absorbent material, that's the reason it's fitting into that category. So there are some that fit into the repels category when they're pure plastic, there's nothing else added to them. And then with regard to stucco, there's a couple of things with stucco I want to clarify too. Stucco, I call the stone that we stick to the base coat of the stucco just thick stucco. Or I've heard other building science engineers call it lumpy stucco. So it's falling into that category of cementitious stucco. So when we have stone, manufactured stone, like I can't think of the brand names right now, but Eldorado stone, things like that, those are classed as a stucco for us because of the design of them. Efus is not a stucco system. Efus is a foam which has a acrylic finish over top of the surface. So, there is some modified stucco materials where we put a hybrid coating on the outside surface, but certainly when we're talking about these, that would be the definition or the distinction. The other thing to think about is not only does it absorb and repel water, but does it drain the water or does it store the water? So we need to talk about that as well, because if you have a very thick piece of exterior cladding and it absorbs that water, that's a good safety practice. So it can hold that water and prevent it from moving forward into the inside. And then it can diffuse it and get rid of it on its own time. Whereas if it's a drain product, then the water that gets through, maybe it soaks into that material, but it gets through the material as well. It drains behind it. It's got an ability to get rid of the moisture that way. So as we look at the various claddings, like in this particular building, I noticed that it's got 3 different claddings here. So if we look at the cladding on the left, we've got lap cladding, lap siding, we've got stone, we've got shakes up at the top, we've got panelized at the bottom. They use just about every type of cladding is available. So when we're talking about claddings, I thought, let's break it down into a simpler aspect, because in a lot of cases, what happens is we have probably 50, 60 different options in terms of cladding. I'm not sure why my screen wants to jump like that. But instead of breaking them down into, this is vinyl siding and this is stucco and this is this, I broke it down here so that you can look at the lap siding. So horizontal, vertical, it might be hollow, it might be solid. It might be something like on the top right of this picture where you get the Sagiper, I don't know the exact method or the pronunciation of it, but you've got these very heavy PVC type claddings. So those are installed in a way that allows water to drain through, and lap materials like cedar siding or cement based, there's all sorts of different types there. Then we get into panelized, and panelized would be more of the James Hardie panels or board and batten style construction. Masonry, we have natural stone, brick, tile. You can see some tile right here that's put on masonry. Stucco, you've got the cementitious, which is the original lime and cement and sand. And then you also have the hybrids where we add an acrylic coating to the surface. And then the EIFS systems. We have the EIFS systems, which is the full drainage system, which uses a liquid applied. And then you put the drainage insulation on over top of that, and then the acrylic finish or the lamina finish. And then there's also this in the middle, this hybrid system, which has given EIFS a really bad name because the failure rate is very high on this type of a system. So we'll talk about those as well. Now, as we talk about these different systems, I kind of put a chart together and I said, okay, what are some of the characteristics of each of these types? Now, it doesn't flow through 100% because, when you look at the lap siding incorporates a whole bunch of different products. So the characteristics are going to be slightly different depending on the material that is used here. But basically, overall, the lap product is in a way that whatever water gets through can drain out through that joint. Does anybody remember using oval-headed nails? Oval-headed nails were designed for cedar siding. So you'd nail the siding on, and then the next layer that came over it, the oval nail held it away from the first layer. So it created that capillary break, or that space where air could move in, water could move out, and air could dry the cavity. So, there was a product that worked really, really well. And we recognized that water would get trapped in there. So we needed a space to let moisture escape. And that's what we chose to use. So we don't see that too much anymore. But the idea of this is we've got good drainage. It resists wind-driven rain really well. It's got drying capabilities where air can get between all of this. And sometimes it's vapor impermeable like with vinyl, and sometimes it's a little more permeable. But at the end of the day, because of the air blowing through there and in behind there, it's got the capability that even if it is a vapor barrier, the air will get rid of the moisture and the accumulation. So that's probably our most common type of product, is the lapped. Panelized is another one, and panelized is very poor in terms of drying ability. There's just no way for air to get behind there unless you put a vented airspace behind there. So if you strap the wall over top of your weather barrier, and then you put the cladding over top, the panels over top, then you get good air drainage, air space in there for drying, and you get good drainage as well. But this one needs good drainage. You need some way to get the water that gets behind there to get back out. And so that's an important aspect of this. For this to perform, it's got to have really good drainage. There's a risk of hydrostatic pressure if it doesn't drain. So water gets in behind here. If you get water that's building up and getting into this location and it can't get out, it's just going to build up and create a hydrostatic pressure and push itself in through staple holes and joints and overlaps. There's a little bit of expansion contraction, and it's semi-permeable, I guess you would say, depending on the product that you're using. If you're using a good one-side paper-backed, it doesn't meet the vapor barrier requirements. It does meet them. It actually is a vapor barrier, whereas if you use more of a James Hardie, the cement panels, they are just above that vapor permeability rate. If you look back at the original or the traditional masonry, you see that you've got this great big airspace here in behind. So that gives good air drying ability in behind. It gives the ability for the brick to hold the moisture and release it slowly over time. But that also means that you've got a risk of vapor drive. And what a vapor drive is if this is soaking wet and the sun blows, if the sun shines on it, then it expands the moisture in there, it turns it to vapor, and it drives it back into the wall. So a vapor drive is not a good thing. So when you're looking at putting a house wrap on in conjunction with this, you want something that's going to resist that vapor drive if you have the potential in the cladding to absorb moisture and hold on to it, and then the sun shines on it. It's got good ability to resist driving rain because this creates a bit of a pressure boundary in between. And so when the air blows in between, you get a high pressure on the front, high pressure on the back, and it equalizes and limits the amount of water that gets in there. And it's a semi-permeable material, so it will dry over time, even through the materials itself. But that brings up a good point. When we're talking about air transport or wind-driven rain, if you look at this illustration here, on the left, we've got wind blowing against this house wrap. So the WRB or the house wrap, and we've sealed it. We've put tape on all the joints. Now, the wind blows the rain against it, the rain sheds down. But because there's a wind pressure on this side, we have a high pressure, and because there's no wind on the backside, we have a low pressure. So what is that called? That's called a suction. So any discontinuity between, or any defects or holes in that poly or that air barrier is going to allow water to get sucked in. We can offset that a little bit if we put a lap material on in this situation. So here we've got a lap material. The air can blow through, and because it has to go up at least 4 inches to get into the building, it hits the sheathing, got nowhere to go, so it goes up and down, and that creates a higher pressure behind it. So high pressure here, high pressure here. So that little staple hole you have here, it doesn't end up sucking moisture through. So that's the principle behind putting that pressurized cavity like you see with a rain screen system or a brick system. When you're looking also at a lap siding, for instance, and you look at the rainwater hitting here, we get the same situation. We've added the siding to the exterior. Now when the water's shedding off the surface, any little beads that are sitting at these joints, the water will get pushed up in behind because the air gets pushed up in behind. But the more air we let go in there, the less water gets pushed up and the less capillary action. So the combination of suction from the pressure differential of the air and the suction of the capillary where water sticks to itself is reduced. But because the paper or the house wrap is right behind here and it's a high-low pressure, we still have the same risk of water in contact there. Whereas if we put a vented space, if we put 3/8 strapping on here first, and then we leave an airspace, then whatever water gets pulled through here, it sits on the backside of the cladding and just runs down and drains out. So the venting isn't just for high rain areas like Seattle or Vancouver. The venting works good when you have high wind pressures with rain and where you have a material that needs to be dried, such as a cladding that has very low vapor permeance. So if we continue on, we talk about a stucco type cladding. So this is 2 stucco materials here. We have this stucco material, flat surface finish, and then we have the bumpy stucco or the stone. And the reason I call it that is because if you look at this diagram here on the right-hand side, you see that the base coat of the scratch goes on over top of a double layer, usually of tar paper, and then the stone gets embedded into that. So the base coat on stucco is exactly the same design as the base coat on the stone for manufactured stone. So that's why I call it the thick stucco. But its ability to dry is terrible. The air doesn't go through there. And particularly in here, when you have a cementitious material and it absorbs water and then the wind blows over it, it's sort of like, you look at this, we talked about the difference between a Tyvek suit and a cotton suit. If you're sweating and that material absorbs the moisture, when the wind blows, it dries out. Well, it's the same thing with your stucco. If your stucco is a sand and cement based, and then the wind blows over it, the surface is exposed to the wind and it dries quicker than if it's got an acrylic finish on it. So the acrylic finish, that hybrid, just adds to the risk there. Everybody thinks it makes it better. It actually makes it more difficult and harder to perform correctly. But it's got a lot of things that kind of go against it. So it's got poor air drying capability. It needs lots of drainage. There's a high risk of hydrostatic. There's a high risk of vapor drive. It's got hydric storage, which is absorbing water. And so if you think of the water that gets in around this window and then it's draining, it's got to get out right here. Because if it continues down, it's going to end up in this door and so on. So all of the characteristics of a stucco or a manufactured stone product mean that it's very, very susceptible to moisture issues compared to all the other products that we've talked about here. If we look at the difference between a stucco product and an EIFS product, the EIFS product, or exterior insulating finishing system, it is able to deflect the water that's on the surface here. And if you look at the cross section here, it's got really good drainage because it's got this geometric design in behind. So this foam is attached to the liquid applied barrier. So the water air barrier is liquid applied, it's put on as a liquid, and then you put a notched trowel. So it puts grooves up and down. And then the foam itself has a geometric design in the backside. So when you put the foam into it, you have the notch trowel grooves, plus you have the notches in the foam to overcome anywhere that the foam might, get filled in with the mortar that's in behind there. So it lets everything drain quite a bit better. So these systems perform fairly good. They have really good drainage. They don't have very good drying. So to get rid of moisture when it's trapped in this location here is very difficult. They resist wind-driven rain really well, and they're semi-vapor permeable. So it's not waterproof, but it is water resistant. Now I thought we'd just jump back and have a look at this one here, vinyl lap siding. One of the reasons is this product performs the best out of all of those when it comes to building performance. When it comes to hail, not so much. Cost, retaining its color or its finish, maybe not so much. But when it comes to building performance, it performs really, really well. And the reason is all these big air voids in behind it. So we nail it on here and we leave that a little bit loose so water can drain through. It creates a pressure differential between the front side and the back side. So if we have a high pressure here, there's enough air that gets behind it to create a high pressure here. And so that reduces the suction where water can come in. And because there's so much air that's in there, it dries really, really well. Even though it's a piece of plastic, so it's a vapor barrier, there's so much air that gets in there that it dries extremely well. So vinyl siding, believe it or not, is one of the best performing products when it comes to, keeping a building dry and keeping the water out. So that's what I would use when I'm looking at, an assembly. I'm looking at all of these characteristics, and rather than just use the exact same thing on all of them, I want to assess what they're going to do when they put them on the exterior. Now, what that means is I want to look at the weather barriers. What goes on behind it? Do I need a liquid applied membrane, which also acts as an air barrier? Do I want a self-adhered membrane? Maybe a peel and stick that I put on there that's a vapor open material, but stops the liquid. Maybe I want a house wrap, or maybe I want a tar paper. What we use on there is dictated by how much moisture is in here. So for instance, with stucco, where it's going to hold a lot of moisture, if it's holding the moisture and we put a tar paper on, that's allowing the moisture to wick through. And then when we look at the assembly itself and we look at these components here and how they deal with moisture, and we think, okay, we've got the system down there. Then when we get into the sheathing, what's the best sheathing to use underneath stucco? Is OSB the best option? Probably not now at 80 bucks a sheet, but is OSB a good option, or would we be better off with maybe some fiber boards or some dense glass, some drywall, something that's going to breathe or resist moisture a little bit better? So when the moisture gets in the stucco and it absorbs through the tar paper, what's the material behind it? Is it highly resistant to moisture, or is it not very good when it comes to moisture? So I want to balance those together when it comes to this. And what's the wind-driven rain capabilities? If you're in an area where you get tons of wind-driven rain, then what's the best material to tie in there? And even your air barrier, when you're looking at an interior air barrier and you think of how much wind that's going to stop, that's going to move the pressure plane as well. So if the pressure plane is on the interior where the poly is, and the air on the outside can move freely through both the cladding and the sheathing, then the pressure drop is on the inside where the poly is. Well, where's the water? Well, it's safely drained on the outside surface, and even water that gets through the outside to the second plane, which is your weather barrier, the water there doesn't get sucked in because it's all an equal air pressure. So when we look at the whole assembly and we look at the aspect of the air barrier, see here we have the exact same situation we looked at before, but if this is really, really robust, this is a very strong air barrier, then we can have a high pressure here, we can have a high pressure here, a low pressure here, but water never reaches this surface, which is my pressure plane. And the water wants to get sucked through a pressure plane. So we want to keep this high. We want to keep the second plane high. We want to have the sheathing stay high pressure, because when the pressure is equal, there's no suction. So when we're looking at the assembly, those are things to think about. I know for years, I always thought that a rain screen, like putting strapping on like this, only had to be done in Vancouver. We're way too dry for this. But that's not really what it's for. It does help the drying ability, but a vented space like this, it can be used for drainage. It's a capillary break, so the moisture that's in the cladding doesn't contact the wall. It can be used as venting. It can be used to dry the sheathing if the sheathing has the ability to get wet. So when you look at all of these components here, you know, it relieves hydrostatic pressure. There's a pressure imbalance there. So the pressure stays low on the inside of that, but on the outside, the pressure stays high on both sides of the cladding. So there's no suction as well, like we talked about. It's hydric redistribution. That's a big one when we're talking about stone, when we're talking about stucco, when we're talking about materials that absorb water. That hydric redistribution really means that the water will soak through and move in all directions as it's drying. Not only is it drying outwards, but it's soaking into the materials around it. So there's a lot of a benefit of that. We talked a little bit, well, I guess we talked a lot about it last time. We talked about this MOP principle, the moisture opening and a pressure. So following in that aspect, when we put a wall together, a building together, that assembly, we want to look at those three components. You know, we're protecting against rain, snow, and vapor. But now here's the openings that we need to worry about. On an opaque wall, it's rare that you would ever have a leak on an opaque wall. It just doesn't happen very often. You don't have a window or a door or a vent or a pipe running through. You know, the ability of water to get through is really low. So we look at soffits as an opening. We look at fenestrations, windows and doors. We look at penetrations, you know, pipes that run through the wall, and then the base or the bottom location where the siding terminates. Those are areas where moisture can get through. So we apply those principles, moisture opening and pressure, to those areas. We also look at wind and its ability to move moisture. We look at the hydrostatic pressure when we get a buildup of water or liquids, that hydraulic pressure that pushes it through, and then vapor pressures. When we have a high vapor pressure, it wants to move from one side to the other. So that's the pressures of the force that we're talking about. And then ultimately the drying. If something gets wet, it's not the end of the world as long as it dries reasonably quickly. And we know that from washing our clothes on a semi-regular basis. So those three things, the moisture open and pressure, lead to this, which is the moisture balance, moisture in, moisture out. So if you think of cladding, and you have the ability for a cup of water to reach into that opening and down the second plane. Well, if a cup of water can go in, balance would be a cup of water can leave. Teaspoon in, teaspoon out. 100 grams of vapor in, 100 grams of vapor out. So we keep that moisture balance so we don't damage things. So where does it start? Starts at the top, at the soffit. So do we put something in here so that if we get wind-driven rain coming through the soffits, depending on the amount of wind, depending on the height of the building, depending on where our roof vent opening is up here, if the air comes through here, it wants to leave through that roof vent, it can easily carry water at this point. We've seen it sometimes 4 or 5 inches. If you look at apartment buildings, you know, a 4-story wood frame apartment, seen easily wind carry water 4 or 5 inches up there. So if you don't have the second plane of protection up in that location, then that can create some problems for you. But this also vents this location here and keeps this area relatively dry. If we put a closed material here, even if we don't get a lot of air leakage from the building, we risk having moisture accumulations in this location. So there's a couple of reasons why we have that. This is the gable end side. This is again a protection in terms of air being able to move, but stopping the water. So if this is the closest location and the wind pressure is like this, then we put a little piece of house wrap there over top of this one so that it picks up any moisture that the wind is blowing instead of blowing it straight through and into the attic here. So just little things like that that can help. If we have no soffits or we're doing a side yard, a cantilever, this piece of rough fascia, when we look at that piece of rough fascia, it's got, you know, if we don't put a piece of house wrap behind it, something to tie in, a building envelope tie-in detail here, then when the water hits this corner right here, it goes right behind the paper that's on the wall. So that's another location of entry at the top. We're dealing with parapets. If we have a flat roof, parapets, the waterproofing membrane needs to come up, over, and around. Now, the waterproof membrane, I would rather it connected to the second plane and behind. But in this case, this still works as long as we have water. When it gets behind, up and behind the coping or the metal cap, we want it, as it leaves that, we want it to drain down and outboard of the second plane of protection. So rather than just cut this off and get rid of it, it's got to lap over so that we pick up that moisture from wind-driven rain locations. Penetrations, when it comes to second plane, we always want to seal it here and here, but we also want to stop the wind and the air from blowing through here and here, depending on what our pressure situation is. So different claddings are going to perform differently at that location. But the trick is here, limit the entry of moisture, and whatever moisture is already here, seal it out so that the water that's running down the second plane doesn't enter in around that pipe or that duct. In terms of windows and doors, you know, in a lot of cases, we used to put nothing into the rough opening. Like here, you can see there's nothing, right? But we know that that's not the best way to build. And so the codes have changed over the years. And now we're required to meet the CSA A440 standard, which is we have to protect that opening. So we put something in there in the opening and we treat all our windows and doors as porous. If we treat them as porous, we can't go wrong. So I've heard it said there's two types of windows, those that leak and those that will leak. So nothing against window manufacturers, but windows fail. Glazing fails. Water gets in from other sources. For instance, if you had water come in through the soffits and run down the backside of the sheathing and it leaked out right here on top of the window, it's going to run down the two sides and it's going to end up on this sill. So we leave the sill open to drain water out, but we also try and protect it from water coming in. But what happens sometimes with various claddings, for instance, here we have the first plane, second plane. If this was a stucco material and it was a hybrid stucco, we would put the stucco right down to the flashing like this. And because the acrylic finish is almost like a sealer, if we put the acrylic finish over the surface, it gets bonded to the flashing. Where's the drainage? There isn't any. So that might have performed perfectly fine with cementitious material when it shrunk and it pulled away, but now we have elastomeric type sealers and acrylic finishes that don't pull away. And so we've eliminated the exit point that was in the old stucco by sealing up the new stucco, and we need something there to create that drainage point. So depending on the materials that we're using, we need that to be able to get rid of water. So for instance, here we might have the bumpy stucco, the manufactured stone. Well, down here, there's our entry point. If we don't seal that lower flashing to the window, the water gets in behind here, which is fine as long as it can drain. If you get half a cup of water into that, as long as you can drain a cup of water away, you're fine. But what usually happens is you get enough water in here and it can't drain, and then it builds up a hydraulic pressure and pushes it back into the wall. So, you know, there's options such as this where we add some drainage here by taking this window bib and draining it over a flashing, throwing a batten in here, and then putting the flashing in. And now if water gets behind here, it just recycles it and drains it out at this location. So it's thinking about how we handle moisture and the type of cladding we're using and what the type of cladding is able to do when it comes to handling moisture. So again, at the base of the wall, and it sounds like I'm picking on stucco and bumpy stucco, but these are the ones that fail the most. Vinyl siding the least, manufactured stone the most. And a lot of it has to do with the fact that we don't treat this stone the way we treat stucco. Stucco needs a casing bead right here. The casing bead goes over the paper goes over top of the flashing, and the drainage is right here. And if you eliminate that drainage, you get a hydraulic pressure that builds up and it pushes through and back into the building. And that's what causes failure a lot of times. Not to mention the fact that if you look at this detail here, this is your second plane of protection. I'd be getting a new stucco guy because that's just unacceptable. You have so much opening there that you're going to drain a ton of water in. Now look at the heights of this building here, right? You've got 3 stories with this kind of workmanship. And then we add to that 3 windows. Let's just do a little bit of quick math here. This window, for instance, in this drawing is 60 inches, 5 feet. I have an 1/8 of an inch gap all the way around here, 1/8 of an inch gap here, 1/8 of an inch gap here, 1/8 of an inch gap here. Now what's going to happen? Well, moisture is going to get in and around potentially. So I have 30 square inches, 1/8 of an inch times 5 feet times 4. It's 30 square inches for that window, and that window. So now if water gets in here and it drains down, if it happens to drain over this way, it gets kicked out by that window. But if it happens to drain over this way, it collects with this water and it collects with this water. And this area here gets a huge buildup of pressure because the water starts to climb up. And then it goes back into this point, and now the water's back into the building. So lack of drainage is one of the biggest killers. So when we're looking at drainage of these types of materials, you know, where we embed them into this adhesive, we've got tar paper behind there, but how does the water on the tar paper actually drain out the bottom here if we don't give it a space? So that's one of the particular aspects of stucco and or manufactured stucco that's so critical that we give it drainage. Efus is the same thing. It's not the drainage on the plane that we worried about, it's the drainage at the surface or the base, the top of the window. The exit point has to allow water to escape. So when we don't allow water to escape, we get things like this. Let's see if I can get this to play here. Right, so we get this buildup of water. Now, somebody spent a lot of money in Blueskin. It did absolutely nothing because it let the water get behind the stone, but the water didn't drain all the way to the bottom. This particular building is a 7-year-old building. It's a 4-story wood frame building. And, you know, there's a significant amount of damage on this building because of the way it was put together. So, you know, we need to look at the assemblies, not just the product or the cladding, the assemblies and how it resists moisture. So let's go back to these assemblies again. Let's look at brick. This is a brick house and it's a gorgeous house. It's beautiful, but they had water every time it rained. The water would drip in and it would drip through the soffit down below. The problem was there was no sealant right here. We seem to have an aversion for sealant in newer construction. You know, the building code says that you have to put caulking and sealant at every connection between the window and the cladding, and we generally don't do that. But here we have a 1-inch space behind the brick, but along here, you know, we're getting all the water that's shedding off the surface. This has a bit of a slope to it, but the rain is hitting this surface as well. So if it overwhelms the surface and it drains back in, and then if it can't drain out quick enough, it's coming back into the building. Stone is the same way. We see failures with stone all the time. Here you've got some catastrophic failure. This started at the soffit right here. The water, this is the line of the soffit, which is exactly the top height of the wall. The paper didn't go in behind the soffit, so the water hit this surface here and it ran around the joint, and now it's behind the paper. And when it got down to the windows are sealed at the bottom, so the water can't get out. So everybody wants to seal things from the outside. That doesn't work. Water will find a way in. So if the water gets in, we treat these windows, these doors, these fenestrations as porous, then we can drain the water out instead of trapping it. And then from there, the cladding needs to do its job to drain water. If you see something like this, where you see all this efflorescence, see the indications that it's trying to drain here. but you got all this efflorescence here. That's a lack of drainage. So the water that gets in there, now it soaks into the stone, it soaks into the stucco base, it soaks into the OSB. And then as it starts to dry, you get that hydric redistribution. In other words, it starts to spread out, the water spreads out. And as it does that, it creates this deposit of salt on the surface as it's evaporating. And the wetter it is and the longer it takes to dry, the more salt you get, that efflorescence buildup. So there's strong indications of what's going on there. This example here, we had a hybrid stucco. So what they put on here was a house wrap that ran down to the tar paper where the stone is. And the house wrap was covered with a 1-inch foam that was mechanically fastened. It was nailed on. There was no drainage between it. But the water was getting to that surface, and as it drained down, it was draining behind the stone, which had no drainage ability at the bottom. So this is the rim joist, this handful of material right here. And this is my finger going into that material, 2 inches, because the rim joist was completely rotted out. So if you let the water in and you don't let it out, that's where the problem starts. So coming up with these hybrid assemblies can create some problems. If you look at this assembly, this is a true EIFS. So it's got the geometric drainage on the material. It's got a liquid applied membrane on it. But where this one failed was the exit point down here at the bottom. Some of these decks had stucco at the bottom. Some of them had the wood at the bottom. But you can see the damage from not being able to drain. So the water's getting in there and it's flowing out this way, but it can't escape. So down here, the water, here's your membrane here. The water is trying to escape out. When we went around the building, you can see the efflorescence building up here. But see these pins we put through the foam into the cantilever, it's 100% wet. It's saturated, and you can see the evidence of the staining at all these intersections. So it's the tie-ins that created the problem. This is a good rule of thumb here. If you seal it out, you also seal it in. So make sure that the water that can accumulate in there is allowed to escape. So traditional stucco, in this case, with a hybrid acrylic finish on it, creates problems like this. How is that stucco going to drain? So it really comes down to how much water gets in behind the stucco. So the acrylic does limit the entry, but you still have soffits, you still have windows, you still have other penetrations above there that lets the water in. So you need to let it out. So in all these cases, when we take these buildings apart 4 or 5 years down the road, you see all sorts of black sheathing. It might not have failed and started to deteriorate, but it turns completely black, and you can see that the water is accumulated there and hasn't drained. And then we do things like this, where we put battens on with square shoulders, or we put something like this on that's completely flat and it sticks out 10 inches. And there's no way water is not going to sit there and accumulate wet snow, spring and fall, and it goes right into that window. So lots of little things like that. When we look at this type of material, what's the danger with a panelized material? Well, the one thing about it is it's fantastic for drainage. It's got huge amounts of airspace, very few contact points with the wall, and it's all vertical. So in terms of performance, it performs excellent, but it doesn't perform excellent when this material here is 120 degrees and you put it on top of a plastic material, and after 4 years, it gets brittly hard. So when the air blows, it just crumbles. So is the material suitable for this? Is the cladding behind the material, is the wall assembly suitable in this case? This particular design calls for tongue and groove, and they put it straight over the house wrap. But on the interior, they went with a standard 6 mil poly. So they didn't have a super airtight interior, so the air blew into the wall cavity, and then the air blew out through the exterior walls. Well, as it did that, it soaked into the vapor, and the moisture soaked into the wood, and the tongue and groove, because there was no air movement through it, the tongue and groove just swelled and made the opening close, or made the opening smaller. So now the air for sure couldn't get behind there to get rid of the water. So in these cases, having a good air barrier is critical. So maybe we look at the house wrap and we go, well, that's not the appropriate product for this. We need a liquid applied air barrier. Or we put strapping on here. We put something that's going to allow the moisture that's trying to escape a place to go. So we separate the two, we let them dry. So when we look at panelizing walls, it's not just for high water, it's also for humidity, drying, it's to change the pressure differential within the wall, so when there's wind-driven rain and so on. So you look at this assembly here and you see the tongue and groove right over top of the sheathing. The same principle applies to something like a panelized product. Either product, when they don't have the ability for air to go through and for air to dry them, if this material here is 12 nanograms, what does that mean? Well, that's about a quarter of a perm. A perm is 60 nanograms. A 60 nanogram is what you can use for a building or for a vapor barrier on the interior of the walls. So these materials have very low opportunity for vapor to escape. So they rely on air drying like vinyl. So if you sealed up all the holes in vinyl and put that on the outside, that's basically what you're creating here with some of these panelized products and drained and vented products. So panelized materials like this, these ones also added, in this particular case, you have very low air flow in behind. You have a panelized product, but then they went and added a foil back insulation to the wall. So you can see the end of the screw is completely rusted. Well, the sheathing would have been saturated, soaking wet, because the foil is a vapor barrier. You got a vapor barrier on the inside with your poly. Moisture that gets in there gets trapped and it can't escape. So in this application, this was a very poor assembly. It wasn't just the fault of the insulation or the cladding or the wall. It was a total failure on the whole assembly because it wasn't well thought out in terms of what's the best way. If the customer wants insulation and they want this panelized material, what's the best way to give that to them that will perform? So panelized Tng, we show this over and over just simply because of the failure rates with it. And you know, on big custom fancy houses, people love this type of solid material. If you look at the soffits here, you know, what's the risk of air from the house leaking into the soffit? It's pretty high, but this is a build on at the top. You're assuming that there's no air leakage in here, but never assume that. Even the tightest homes in the world have some air leakage. Passive houses have air leakage. It's just small amounts. But if they all happen to be in this location where you put a tongue and groove material, then that's going to lead to failure. This was a man-made tile. I really can't remember what the product was called, but whether it's a man-made tile or whether it's a granite or something fancy like that that people put on their house, the way this is designed is we have this sealed barrier. So all the joints are caulked. But what you can do also is you can leave some of those joints open for drainage and airflow. Because again, the idea behind this one is we want the air, see here's the drainage plane right here, but we want the air to get through and create a positive pressure on the backside so that there's no suction. So the design of this assembly is very important. You know, how do we create a good air barrier at this location? We want to use tar paper. Why? Well, there's a specific reason for that. Do we want to use house wrap? Should we use liquid applied? What's the difference between them? So rather than just go for the most economical or the most cost effective, look at what it's supposed to be doing when we put this together. This is a $5 million house that we've been working on. And you can see up here, it's got these 45-degree soffits. Well, it's got a flat roof. It's all spray foam, the whole thing. But when we took the speakers out here, there's no airflow in that cavity, zero. So they've sealed it. They've put the stucco on the outside and sealed it all the way up to the top where it connects to the roof parapet. So there's no air leaving. But the spray foam isn't that airtight. So it's more airtight outside than inside. So the air that blows through there is building up moisture and it's starting to deteriorate. We're getting all this mold growth within the cavity of this assembly. So looking at the whole assembly and saying, well, we don't really need ventilation for the roof. The roof is taken care of. Well, do we need ventilation for the potential of air leakage into that space? Or maybe we should put a liquid applied membrane on there rather than just straight tar paper with stucco. So getting into these different materials, if you look at this application here, let's get this to play. This is what we call a hybrid stucco. So they put on a house wrap, they put a 1-inch foam with no drainage, and then they put an acrylic finish over top of it with a mesh. So here they didn't seal the entry points. Every deck was wide open for water to get in there. They had soffit entries, so water was getting behind the soffits. Look at the staples, how rusty those are. You know, and everything that's in behind there is getting trapped. And that's a 3-story wood frame building. So the drainage at the top, the water that's getting in the top and at the windows and at the decks above has to go all the way down to the base to escape. And that's just not realistic, because as it leaks in at the top, it's also leaking in at the middle and then at the main floor. And now it's all expected to drain out the bottom. Well, you need some midpoint drainage on that. You need to look at that and say, hold on a second, has that got a moisture balance? Are we going to get water in? How do we get it out? Do we have to bring it to the bottom, or can we bring it out midpoint? Could we put a through wall flashing somewhere in the middle? That's where some of the EIFS products are so advanced compared to the hybrids, because a liquid applied like this will resist hydrostatic pressure. So you put that onto the wall, and if the water's sitting behind there, it's designed to drain out. So you have these little grooves within the foam itself, but then you also put it on with a notch trowel, which gives you an additional space for drainage. So these, we treat the windows as porous. We put the window in and we seal all the way into the rough opening. So this membrane gets applied to the rough opening first, then the window gets installed, it gets taped and sealed around the perimeter. The bottom is open, like you can see here, and then the reverse flashing goes on. So if water comes in here, this is going to get caulked at this point. All the way along there, it's going to get caulked to reduce entry. But if it does enter, it can freely drain behind, because you have all those drainage grooves down behind that stucco. So an EIFS system as a full system performs extremely well, because it's designed to handle water correctly. A lot of the times what we find with the claddings is it's not so much the cladding itself, but it's the transition from one type of cladding to another type of cladding. So if you look at this cladding here, you've got board and batten, you've got shake up here, you've got vented up here, stone down here, and then lap siding here. So what details do you give to the guys putting this together? How do you transition? How do you deal with water that's trying to drain out the bottom of the stone, drain out the panelized locations here? Or do you just do the exact same thing all the way around? You know, when you look at the bottom of this window here, where the stone is below the window, it's supposed to have a 2-inch space. The manufacturer requires a 2-inch space between the stone and the top of the roof, or the front door, or any other solid surfaces. You got to have a 2-inch space. So if you don't follow the manufacturer's requirements, then when you come back to warranty that and you have a failure, then that's going to cost you. That's going to come out of your pocket, because you didn't meet that requirement. But in any event, you want to take responsibility for this, because you want to say to the guy putting it on, this is the way I want it done. He might have been doing it for 30 years, but we all know people that drink and drive, and just because they don't get caught doesn't mean it's right. So we want to look at the way that we address this and get rid of water. You know, you look at one like this. This one's got the tongue and groove on the soffits all the way along. It's got flat roof. It's got stucco on the sides. It's got panelized on the sides here. And then it's got these panels underneath that go down to the grade. So how do you tie those together? How do you make sure that this isn't letting in way more water and then letting that behind the stucco, which has less of a drainage than this upper panelized material? You know, if you're building big custom homes like this, that could cost you a fortune. Sometimes we're seeing this build out as well. You know, when it comes to these interface details, this complex cladding, you get these build outs where you stuff a window in behind here and you build the wall out. Well, now you've got a double layer of OSB. OSB is a vapor barrier. But what about the water that potentially can get in at the sill of the window here and run down in behind? Have you addressed that by looking at this location here? So where's the drainage plane? Have you identified it? Are you making sure that the drainage plane is the glass out over this sill and down the face? Or have you adjusted and considered that there's some incidental moisture potentially in behind here? Maybe you need a more robust barrier at this location. Maybe a liquid applied barrier is much better than trying to use a house wrap and trying to deal with water. So having those details Details, details, details is so critical to dealing with moisture. Having something like this, see this particular detail, sequencing, manufactured stone installation before cladding. So if this is the first guy in, he knows he's got to extend his paper up to tie in with the house wrap above. This guy knows that if I'm sequencing it this way, where I'm putting the stone in first and vinyl after, I need to intersect the vinyl, or sorry, the house wrap, the tar paper, whatever I'm using in behind with the tar paper of the stone. And it gives me how to do it. It tells me what to add. It tells me the reason for it. I need cladding to be able to drain at those locations. So when we look at the transitional details, like for instance here, you know, that flashing is designed to pick up water that's behind the second plane coming all the way down and trying to escape. Well, they squished the flashing between two pieces of batten. There's no way it's draining anything. So the risk here is high compared to if you put that up 1/4 of an inch and let it drain out. If you put that in your specs, then you can tell them this is what I want. You can put the details in there. If you look at this one, they're going to put an acrylic finish over top of the surface, but there's no casing bead here. There's no drainage ability. So when they put the acrylic on, it's going to bond to the top of the flashing and no drainage is going to occur. So when we look at these kind of assemblies, you know, here we've got tar paper over top of the wood section. There's a concrete section here. Well, when they put the adhesive on here for the stone, for the bumpy stucco, it's going to bond to all this concrete. So now the water that's supposed to drain out, it gets to this point, it can't reach the flashing down below. So remember, that's bonding to that surface. Well, now the water that's getting in from the upper locations here has no way to drain out. So it's all about details. So I'm going to wrap up today talking about one job here, which kind of hit the nail on the head for me when I looked at this job. This is one where we have these multiple claddings. So they got stone on here, they got lapped cement board here, and then they've got lapped battens up here. So the smart battens. What's the vapor permeable, I guess the vapor permeability of a 3/4 inch smart batten? It's pretty low. What happens when you build it out and you put a layer here and then you put another layer here and then you put another layer here? Well, pretty much non-permeable. So moisture that gets behind there, how's it dry? Well, it doesn't. So you're assuming that maybe moisture is not going to get behind there. Well, when moisture does get behind here, it takes a lot longer to show up. So the homeowner started to see staining on the ceiling. They started to see water collecting on the sill. They started to have the tiles on the floor started to lift in the exercise room here. Once it started to come apart and we started to look at things, we found that, you know, the joists were completely rotted out. This is the OSB sheathing here. And on the outside was stone, on the inside was spray foam. They had put 2-pound spray foam in between the cavities, thinking that that was the way to go. And it works, it's fine. But once you trapped it in there and you let water into that location, there was no drying ability whatsoever. So interesting how when you look at this picture here, where the thick stucco was, where the stone was, and where the lap siding was, you can almost exactly see where the product was draining, where the product was not draining. Up here at the top, we had a little bit of a leak at the scupper. We had some water leaking in here where the multiple layers of smartboard were. It rotted out through the front, this whole area here. You could look right inside. There was no venting on this roof. They put an airspace for venting, but they actually hadn't tied it to any venting. But the biggest problem was the spray foam on one side tied to the sheathing, the stone on the other side tied to the sheathing, and then the water gets in there. Well, it's not going anywhere. So the absorption just continued in through. So the two materials that went together were causing problems. Even something simple like this, you know, you put the smart batten in contact with the concrete gets wet, absorbs water, it absorbs into the smart batten. Why not put a spacer between it? Put a flashing, put a couple of pieces of treated lumber, set the post on treated lumber, and then leave yourself a little bit of a space for water to drain out the flashing, but also prevent that material from wicking the moisture up. That's a structural post holding at the deck. So the assemblies, sometimes we don't think about them. We think, well, that's on the outside, no big deal. You know, you can you can replace that post. But what's happening to the 2x6s, which are untreated, which are sitting right on the concrete? So long-term, we've got to look at the long-term effects of this and how it's performing. And so when we go back to this chart and we just look at the different materials and we look at their different capabilities, we want to take this information and use it and apply it to the assembly that we're building and say, what's the risk of it holding water? You know, what's the hydric storage? Or what's the risk of a vapor drive occurring? Or what's the risk, you know, of drainage not occurring? Maybe I need a different sheathing behind that so that it's more robust and able to resist. And so in conclusion, these are the three things I want you to take away. Drainage, rule number 1, drainage, rule number 2, drainage to rule number 3, right? Limit the entry based on the drainage and double the drainage to the entry potential. In other words, if at least you're 50-50, if 2 teaspoons go in, you get drainage for 2 teaspoons. Preferably, you have double the drainage than you have the entry, because then when you get that big storm, that big wind, then that can address that and take care of it. So drainage is critical. Remember the MOP principle. Moisture opening and pressure is what it takes for water to leak in, whether it's outside coming in from rain or whether it's inside going out for vapor. And achieve a moisture balance, which ties back to this one. And then number 3, put some details in the blueprint. We see so many blueprints that have absolutely no details. And a lot of builders think, well, if I don't put the detail, then the responsibility is the trade. And that's just not true. Your contract is with the homeowner and with the warranty provider. And that's where it all gets tied together. So if you installed it and say, well, the trade did it wrong, doesn't work that way. Even the building code says whoever did the work is responsible. So you can't rely on the safety codes officer to say, oh, that looks fine, it's passed. You're still responsible. So of the 3 things that I would worry about, those are the 3. And that's the way that you can have a performing building. So that concludes our session. Any questions? I didn't notice any during the presentation, but any questions on anything? You didn't get any questions there, Andre?
Unfortunately not. No questions in the chat at the moment.
Okay. Well, it's not a bad thing. Maybe I actually explained everything.
You hit everything, Darrell. Well, if the last call for questions, everyone. Hopefully, you know, if you have any, I guess you can always send them our way, and we can pass them along. But not seeing any questions. Thank you, Darrell, for another tremendous presentation. We really appreciate you sharing your expertise with us. These have been tremendous, and so thank you for that. And thank you to today's event sponsor, Federated Insurance, for sponsoring today's virtual technical session. And thank you to our partner for this month's sessions, the Professional Home Builders Institute, for being our partner and putting these sessions on for everyone. And thank you, everyone, for again attending this afternoon session. We appreciate your support and your participation. We look forward to seeing you again virtually, but seeing you again soon. We'll keep you posted as we have some upcoming sessions in the works, and when those are announced and the dates are scheduled, we'll be letting everybody know. And so again, thank you everyone for attending, and until we meet again and have another session, stay safe, everyone. Take care. Thank you.